online lab number 4. So in this one, hopefully everyone's found it on Canvas and had a look at it. It's a little different than the ones we've done in the past, because the ones we've done in the past basically give you very specific instructions about, add 20 mils of solution A to 20 mils of solution B, calculate we're not going to be doing that, because in this particular example of a virtual lab, you are going to be the chemist yourself, and basically you are going to have to come up with a procedure. So really it's kind of like, you're doing actual chemistry. You're trying to the way that people who didn't know what the products were going to be when they first started doing chemistry in the first place. Like when the mass of oxygen was unknown until someone measured it. We didn't know how many moles of sulfur reacted with moles of tin till someone did the reaction and actually measured it. So that's what you're going to be doing today. You're going to have 4 chemicals, A, B, C, and D, and adding them together in different proportions and see what the product is, and also figure out what the stoichiometry is. In other words, is it 2A plus 3B makes 1C, or does it make 1D, or does it make 1C and 4D? You have to figure all that out by adding the different components in different ratios and seeing at what point all of the reactants are gone and you're left with nothing but product. And so what we're going to be doing, basically what I'm going to be showing you is, how you get started with it. And then it's sort of just trial and error. I'm going to try this, I'm going to try that. And then what I want for like the last experiment is for you to add precisely the right amount of reactants to get precisely the right amount of products and have no reactants left over. And from that, you'll be able to write the balanced chemical equation, like, 3A plus 2B gives 1C and 3D, something like that. Have everything balanced and have everything in its lowest possible whole number, so you don't have any multiples. So if you can divide everything by 2, go ahead and do that. If you can divide everything by 3, go ahead and do that. So here's the experimental procedure over here. And basically it says you're going to be performing a series of reactions in solution, which is true. So you're going to have 4 solutions, A, B, C, and D. And basically just adding them to a beaker. And you remember the last experiment we did in this sort of, with this particular website. You get a virtual beaker that you put on the desktop, and then when you click on it, it gives you the concentration of everything that's in there. And if you had a precipitate, because remember the last experiment formed a precipitate, it would give you the mass of the solid. Well, here we don't know if the product is going to be a solid or whether it's going to be a product that's still in solution. Maybe it's going to be ionic. We don't know. We don't know if A, B, C, or D are ions or whether they're covalent. We don't know. So these are some of the things you're going to have to figure out just by adding them together. So just by adding one to the other, then clicking on the beaker and seeing what's in there, we're going to be able to figure out which ones are the reactants and which ones are the products by getting the concentrations of them after the reaction's taken place. So for instance, let's say we added the same amount of A and the same amount of B, and then we clicked on the beaker, and it basically said you have a certain concentration of A and a certain concentration of C, but there's no B left over. Then you'd have to say, that means that some amount of probably more amount of B is required for this reaction because it was all consumed. And that B would be the limiting reactant in this particular situation. And that's something we've sort of been talking about in class a little bit. Remember, the limiting reactant determines how much product you're going to make. So if you did this particular reaction, you'd have the freedom to choose, okay, how am I going to pursue that? Do I add more B and see if I get any more product? Is A then going to disappear? And then figure out what's the ratio of A to B. You're going to be given, they're all going to be present in 1 molar concentrations. What does that mean, 1 molar concentration?
Moles over liter?
Right, so each one of them will have precisely 1 mole in 1 liter. And so, and I think you're given like 100 mils of each one. And so when you add them together, you know, remember that when you take a 1 molar of, let's say, of A, and then you dilute it, and if it's now 1/4, let's say you add an equal amount. We'll do this reaction first. You add equal amounts of all 4. So if you added equal amounts of all 4, regardless of the volume, what would be the final concentration of A if it didn't react with anything? So I added equal amounts of A, B, C, and D. Now, if A didn't react, what would be the final concentration of A?
Same. Mm-hmm.
No. You'd have the same amount of A. That is true. You would have the same number of moles of A, but the concentration would be different. And remember, the flask, when you click on the flask, it's not going to give you the number of moles. It's going to give you the concentration in moles per liter. So what would be the concentration in moles per liter? Okay. Equal amounts of A, B, C, and D. I start with 1 molar A. What's it going to be after I've added equal amounts of B, C, and D? Basically, I'm doing a dilution, right? Let me get a... All right, so here's our problem, basically. I've got 1 molar. That's my concentration of A. And remember, square brackets mean molar concentration. And then in my beaker, I add equal volumes. I'm going to tell you what the volumes are of 1 molar A, 1 molar B, 1 molar C, and 1 molar D. So we're going to add equal amounts of each one into the beaker. Now, what is my new concentration of each one of those? They all have the same concentration. If you have trouble thinking, just add a volume. Just pick a volume for each one. Pick, 25 mils or something. Pick 10 mils, pick 100 mils, pick a liter. It won't matter. You'll have new concentrations of each one. Oh, here's my... So here I've added X mils of each one, and now I have 4X mils volume total. What are my new concentrations? Like I said, you could just pick any volume you want. You could pick, let's pick 25, let's pick 250, so your final concentration, your final volume is 1 liter. That might make the math easier. Okay, 250 mils of each one. So my final volume now is 1 liter. What are the new concentrations? I hear some furious clicking on calculators somewhere.
25% for each.
Ah, yes, 25% for each. That should sort of give you a clue as to what the new concentration is. That's a really good point. So if each one is now 25% of the total volume, when they were 100% of the total volume in their initial solution, they were 1 molar. Now that they're 25% of the total volume, what's their new concentration? It's not 1 molar anymore, it's something else.
1/4.
1/4 of,
Molar concentration.
1/4 of what though? You could say it's a fourth, but it's got to be a fourth of something. I'm looking for like a number. I'm looking for the actual concentration. Because remember, 1/4 doesn't have a unit. So if you give any kind of scientific measure, it's got to have a number. 1/4, that's a number, but it's got to have a unit. So you were correct. It's 1/4 of something. 1/4 of what?
1 liter.
Now remember, liter's not a measure of concentration. It's got to be a measure of concentration.
It's a 1/4 of molar mass
1/4 of molar.
concentration.
Well, what was the original molar concentration?
250.
Nope.
Oh,
This is a volume.
one.
That is a volume.
4 molar we have.
4 molar? Was that the original concentration or the new one?
The new one.
The new one. But the original concentration was only 1 molar. How did it get more concentrated when we diluted it?
Oh, okay. I thought we add the all concentration for each material.
Even if we did, the concentration would be the same. So I added 1 molar of chemical A, 1 molar chemical B. Then if I asked what's the concentration of all chemicals, A, B, C, and D, it would still be 1. What's the concentration of chemicals? It would be 1 molar still. The concentration can't go up.
It's gonna be 0.25 molar.
That is correct. That is the answer. Because I have diluted each one of these concentrations here, 1 molar. I've diluted them by 1/4 because I've added each one to the beaker. And so now it's the amount, the concentration of B is now 1/4 of what was originally, because originally 100% of the stuff in this bottle was B. All of it was 1 molar B. Now that I've added it to a beaker with 3 other things in the same volume, it's now only 25% of that original concentration. So it's 25% of the original concentration of B. So if I add the same volume of A, B, C, and D, and then I ask, click on the beaker and ask what's the concentration of A or B or C or D, it'll be 1/4 of what it was originally because I've diluted it by 1/4. And you can calculate this very easily just by taking the original so whatever the original concentration is, so let's take concentration of B. and you multiply it by volume new over volume original. Oh, sorry, the other way around. Volume original over volume new. So my original volume was 25, and my new volume is now 100. So my new concentration of B is now 25 over 100, what it was before. So now it's 0.25, okay? So look for that when we do this experiment, because if nothing happens to the chemical, either A or B or C or D, if nothing happens to it, the new concentration of it will be 0.25 or 0.5 or 0.33, however it is you diluted it. But if some reaction took place with it, that concentration will change. So you'll have to look. So in other words, if I take 50 mils of 1 molar A and add 50 mils of 1 molar B, and I put them together, and then so I put them in my beaker and measure the concentration. My concentration of A is now 0.25 molar, and my concentration of B is 0.125 molar, and my concentration of C is now 0.25 molar. What's happened? Can someone tell me what happened here? First of all, if nothing happens, what would be the concentration of A and B if nothing happened? There's no reaction.
It'd be 50%
50% of what?
of,
Give me a number.
so it's 0.50 molar,
Yeah, right.
0.50 molar B.
So each one would be 0.25 molar concentration for both A and B if nothing had happened. If all we did basically is just dilute them. But that's not what happened. So then we take a look at the concentrations. So we look at A, and basically what this tells me is that half my A was consumed. So half the A went missing, right? It got converted into something. So, got converted into presumably probably got converted into C somehow, right? And then I look at B and I think to myself, 0.125. I was expecting 0.5 molar, but I got 0.125 molar. That's only 1/4 of the concentration I expected. Therefore, 3/4 of the B was consumed. So what I've seen so far is 2/4 of the A is gone, 3/4 of the B is gone, and now I have C showing up. And you use these ratios to try and figure out how much A and how much B create how much C. Am I making sense so far? Because this is pretty much exactly the experiment you're going to be doing. And so you're going to have to think about, what do I expect if nothing happens? And if something does happen, how can I then design an experiment so that when I design it, all of the A and all of the B are gone at the end of it, and all I'm left with is product. And then when that happens, you can then write out, okay, based on this experiment, 2A plus 3B creates 2C, something like that. You should be able to make a reaction that does exactly that. And so you would add, like say, 30 mils of B and 20 mils of A. And so you'd have no A and no B left because they'd all be converted to product, and you'd get nothing but C left over. So any questions on how that's going to work? Because I realize it's sort of, there's going to be a lot of math and a lot of, jotting down of notes and trying to figure these things out. Have any questions on how you're going to approach this?
Yeah, I have a question.
Mm-hmm.
So in order to find how much B went in,
Mm-hmm.
you take the leftover, what comes out as a product of B, divided by what the reactant was.
Yeah, basically you have a look and see how much B is left over. Therefore, you can calculate how much B was consumed. Then you sort of work on, so this much A was consumed, this much B was consumed, and you can convert it to moles if you like, because you have the concentration and you have the volume. And so if you have 1 molar concentration and you used 50 mils of something, you can calculate precisely how many moles that is. And basically that's what you do when you write a chemical formula, is how many moles of A plus how many moles of B give you how many moles of, whatever the product is. So that's how you're going to do it. Figure out how much is left over and therefore how much was used. And if it all gets consumed, figure out, well, if it's a limiting reactant, figure out how much more A you need to use in order for all the A to get consumed too. And then once all the A is consumed and all the B is consumed exactly, and there's nothing left over, then you have the ratio you're looking for.
And if you have leftover C, that's okay.
Well, if you didn't add any C and C is there, then it's a product, right? You automatically know it's a product because you didn't add it; it was created. So that's a really good point. So let's look at another potentiality. Let's say you add 50 mils of 1 molar A and 50 mils of 1 molar B and 50 mils of 1 molar C. You put that in there and you look at the concentration. So you would expect, what would you expect the final concentration? So if nothing happened, again, no reaction, what are my concentrations of A, B, and C going to be?
0.50.
Nope.
It'd be 1/3 of it.
1/3, right? Because I've added 1, 2, 3. I've basically diluted it by a factor of 3. So you take the original concentration, you diluted it by 3, so now it's 1/3 of the original. So what's my new concentration of A, B, and C? If nothing happens, so here's my no reaction concentrations.
16.66 molar of A.
So if it's 16.66 molar, that means my concentration has gone up 16 times. And my concentration can't go up 16 times because I've diluted it. And by diluting anything, the concentration is less, right? So your final concentration has to be less. If nothing happens, your final concentration by definition has to be less because you've diluted it. So if this is our original concentration of all 3 was 1 molar. So what's our final? So this subscript F means final concentration. If there's no reaction at all, what's my final concentration of each one?
Would it be 33?
33 what?
molar.
3 molar of A.
33 molar?
0.33.
There you go, 0.33 molar.
Mhm.
So each one would be 0.333 molar. But let's say that's not what you got. Let's say you clicked on, so you click on the beaker, and what you see is that A is down to 111 molar, B is down to 0.222 molar, and C is now 0.50 molar. What's happened? What reaction would you think has taken place? And you don't have to give the exact ratios, but what reaction has happened here? Something's happened because we were expecting this. If nothing happened, we would all get 0.333 molar for all of them, but we don't. We get something different. So something happened. What happened?
I noticed some like C gain concentration and A and B lose concentration.
That's right. So what happened? So in the beginning, I had equal amounts of A plus B plus C. So I added those together. Then a reaction took place. A went down, B went down, and C went up. So in general terms, what's my reaction? Something plus something gives something. So I'm going to have something plus something created something. That's my sort of general reaction. What's the sort of general reaction without knowing what the ratios are yet?
We decide which is the reactant, which is the...
Yes, exactly. Which two or one is the reactant and which one or two are the products?
When the concentration gain, that's mean it is the product?
Yes, that's right. Because there's now more of it than there was before. So something must have created it. So if there's more of it than you expect the concentration to be 0.333. And then you measure the concentration and it's actually went up. So it's more than what you expected. So in other words, there's the C that you added, and then more was created in the reaction. So we can say that, yes, C is a product. What else can we say from looking at the new concentrations?
A and B, the reactant?
That's right. Because A was consumed, and B was consumed, and then C was created. So if you get a reaction like this, then you can focus in on, I'm now going to add just A and B, and then I'm going to tweak how much of each one. Maybe the first time I'll add 2A and just 1B and see how much C I get. And then maybe you'll have something left over. Either A or B will be left over. You say, okay, that's not the right ratio. Maybe it's 3A for every 2B, and then you tweak that. There's still some left over. Basically, you just have to go back and keep tweaking and tweaking until basically at your final reaction should be, it's like maybe it's 4A plus 5B give 3 moles of C, something like that. So all of the A is consumed, all of the B is consumed, and all you get is C. And then that'll be your final reaction. Got it. I added this many moles of A, this many moles of B, and that's the number of moles of C that came out of it. And D wasn't even involved. Nothing made D. D didn't make anything, and D wasn't created by anything. So D basically wasn't involved.
I have a question.
Yeah.
When you're looking at the reactant and getting 3A, 2B, so is that, are you multiplying 3 times that amount of A? So like that volume of A to get,
Right. Basically, it would mean that I added, so of my final volume, 4 out of, so let's say the total, so I added, so it's 4A and 5B. They're the same concentration. So, so if I added 40 mils of 1 molar A and 50 mils of 1 molar B, I'd have no A and no B left over. They'd both be completely consumed. If I added any other ratio, there'd either be A left over or B left over. So I know that's not the perfect. If I added 3 moles of A or 30 mils of A and 50 mils of B, I would have B left over because A would be limiting in that particular example. If I added equal volumes of A and B, I'd have A left over because it only takes 4 moles of A to react with 5 moles of B. So basically, by changing the amounts, you should be able to figure out exactly what's the perfect ratio of each one. What's the perfect amount of each one so that they react completely? Does that answer your question?
I have another one.
Okay.
How do you determine if it's limiting?
Oh, okay. Here we go. Good question. Let's get a new color. Ooh, orange. I like orange. All right. Let's say I added. We'll go back to the same one. Whoops. So let's say our actual formula is 4A plus 5B makes 3C. So in other words, 4 moles of A and 5 moles of B create 3 moles of C, okay? So what I'm going to do is I'm going to add 50 mils of 1 molar A. I'm going to add 50 mils of 1 molar B. So in other words, I've got equal amounts, right? So under these circumstances, I have more A than I need. Okay, I only need 40 mils of A in order to react completely, right? Because the concentrations are the same. And so my ratio, my molar ratio of one to the other is determined by the volume I add. Because the concentrations are identical. Does that make sense?
So is it the beginning of the number in front of A or B that in turn be like in milliliters?
Well, think of it this way. What do these numbers actually mean? So if we look at this 4, this 5, and this 3, when we write a chemical equation, what do those actually mean?
The ratios
Ratios of what, though?
of how much of each reactant will do that product.
Not giving me a unit, though.
These moles.
Moles, right? Is that what you said?
Yeah.
Moles. That's exactly it. That's what they mean. And so remember, when we multiply a volume times a molar concentration, that's just moles over volume, right? That's what molar means moles over liters. So if we multiply liters by concentration, we're left with moles. So if my concentrations of A and B are exactly the same, I can basically determine the ratio of moles by the volume. So what this means is that 4 moles, damn you. So this means 4 moles of A plus 5 moles of B give 3 moles of C. And it means that in any ratio. In other words, 0.04 moles plus 0.05 moles gives 0.03 moles. That ratio is always the same. I can make this as many moles as I want. It could be as small or as large as I want, as long as the ratio of moles is the same. So because the concentrations are the same, the amount, the actual physical amount, the mole amount, is determined strictly by the volume. And so what I'm basically adding here is a 5-to-5 ratio of A to B. Now I know that the ratio is actually 4-to-5 ratio of A to B. So in other words, I have more A than I need for this reaction. So what would I expect to see? So at the end of the reaction, what should I have? And you don't have to give the exact concentrations, but should A be left over? Should B be left over? Which one would I see more of at the end?
A.
Yeah, I'd only see A, and all my B would be gone, because 4/5 of my A, 4 out of every 5 moles of A, went converted with B to forming C. And how much C would I make?
3.
Yeah, exactly. I'd make 3 moles, and it would be, so my concentration would be
A plus
1.5. 1.5? No, it would be, would it be? I have to figure that out. So A and B and C. So yeah, let's have to think about what the concentration of C would be. It would be, all right, so basically here we would have added 0.05 moles of A, 0.05 moles of B, and we would have created 0.03 moles of C. So our concentration of C would be 0.3 molar. Okay, because we would have created that many moles in a concentration of, our final concentration would be 100 mils, or 0.1 liters. So it'd be 0.03 moles divided by 0.1 liters, and that gives us 0.30 molar. So this reaction would tell you I have excess A. So A is in excess and B is limiting. And so basically what you would do is add less A and see how much less A you can get away with while still consuming all of the B. So let's say next time you added 30 mils. That's a good question. Let's do that. So in this instance, we still have 4A plus 5B gives you 3C. And so in this instance, I have 30 mils of A and 50 mils of B. Now, which one's going to be left over? Is anything going to be left over this time? So I do my reaction. And what happens this time? What am I going to see at the end of it? Am I going to see A or B? I know I'm going to make some C. I mean, it's going to be a reaction. But who's going to be consumed completely and who's going to be left over?
So
B left over, maybe?
A is going to be consumed.
Right, all of the A is gone because we have less of it than we need. We need exactly 40 plus exactly 50. That's what we need. Or 20 plus 30, or 10 plus 15. We need that precise ratio. I'm sorry, yeah, 40. Oh, sorry, 40 over 25, 20 over 25. Anyway, you know what I mean. That ratio has to be 4 to 5. Here it's only 3 to 5. So all of the A gets consumed and there's going to be B left over. So that tells you that at that ratio, 3 to 5, 3 moles of A for every 5 moles of B, that B is now limiting. So that tells you need to add more A. So whatever is left over, you need to add more of the other one in order to balance it out. Because if B is left over, that means B is in excess, right? And A is limiting. So there's 2 things you can do. What are the 2 things you can do? If B is in excess and A is limiting, what should your next reaction do? You can do one of 2 things concerning the volumes of A and B.
Would you increase B?
Well, if you increase B, that means you're going to have even more B left over. Because right now we have B left over and all the A is gone. So if we add even more B, that means our amount of B is going to be even greater and the amount of A will still be gone.
Yeah.
And what you can check for, if I add more B, do I get any more C? And if your B is in excess and you add more of it, are you going to get any more product?
No.
No, C will remain the same. The amount of C will be exactly the same as it was. And that tells you that my concentration of C, the product, now depends on the concentration of A. A is limiting. A is my limiting reactant. So if A is my limiting reactant, what can I do to make it not the limiting reactant anymore?
Increase A.
I can increase A, or what else could I do? That's one thing I can do. Increase my amount of A. Something else I could do too.
Increase B.
Reduce the amount of
Decrease B, exactly. I can either raise my amount of A or reduce my amount of B until the ratio is perfect. And when the ratio is perfect, I will have no A and no B, and I'll only have C. And then when that happens, calculate the number of moles of A, the number of moles of B, and the number of moles of C. And that will tell you precisely what these numbers are supposed to be. Okay?
So I have a question.
Okay, I would expect to be a lot of questions because we've done a lot of stuff here. Yeah.
So if B is an X and is in excess, then
Mhm.
A is the limiting reactant. Is that what
Mhm.
you're trying to say? So
Right, and unless it could be even more complicated. It could be A plus B plus C gives you D. If that's the instance, then you got to figure out, is it A, is it B, or is it C is limiting. Whatever one is, and if you're wondering which one is limiting, increase the amounts of the other 2. And if the amount of product stays the same, so let's say you don't know which one of these is limiting. You don't know whether it's A or it's B or it's C. You have no idea. Do this. Double the amount of A. Double the amount of B. Does the amount of D go up? If it doesn't, C is your limiting reactant. Then you have to figure out, okay, so it's going to be less C than the other 2. And then you have to then, using that, figure out what the ratio of A and B is. Then increase the amount of just one of them and see what happens.
So if you're saying to double A and B, and if it doesn't change D, or if you're still left with some products of A and B, then it's C would be limiting. Is that what you're saying?
Yeah, I mean, yeah, both those things would have to happen. Both A and B, well, A and B concentration are going to go up anyway because you added more of them. But what you're really looking for to see if C is limiting is that do you get more product? If you add more A and more B and you get more product, then C is not limiting. It's either A or B.
But if it's less product, then C is limiting. Then
Well, you won't get less. You'll just get the same.
oh, okay.
Yeah, you'll just get the same. And basically what will happen to the concentration of A and B will just be whatever it was before plus whatever it is you added in there. Okay, should we take a crack at it and see what happens?
Mhm.
Yeah, let's just play with it. All right, so let's share the all right, let's go to all right, can everyone see the virtual lab screen at this point?
Mhm.
Can you see it? So we went to chemcollective.org/activities/auto-graded/112. Oh, and that's the other thing. It will tell you whether you have the right answer. You can put in the answer here. Oh, currently under construction. Never mind. Still working on it. So yes, some of these, and I really like the Chem Collective labs because you can do the lab, get an answer at the end of it, and then you can basically put your answer in. I think the one I'm thinking about doing on Wednesday, you can type in the answer because the lab we're going to do is you're going to do a titration, meaning you're going to add base to acid. And then figure out, what the molar amount of acid, the molar amount of base is. And then you're going to measure a certain mass of acid. And then once you have the mass of the acid and the number of moles of the acid, you can calculate the molar mass because you have mass and you have moles, right? So I think, and at the bottom, you can type in, well, I think the molar mass is, 128.5 grams per mole. Click enter. It'll tell you if that's right or if that's wrong. So you just, keep going back and then you can figure out whether you got it right or not. This one, obviously, they haven't come up with it yet, but all right. So first experiment.
Professor, how you get to this page?
Oh, you can go to the go back to it's right here in the instructions.
I copy that link
Mm-hmm.
and it's it gives me the same page, but I cannot
You say the same page. What do you mean?
yeah, I saw this one. Then what I have to do?
So you didn't, this page doesn't show up? You should get determining stoichiometric coefficients. So you don't get this page, you get something else?
Yeah, but then there is word it comes. There is a message shows up. I saw it shows up to you also as well, but I don't know how you.
So you're seeing the page, but you can't click on anything? Is that the issue?
like I can see that page, but in the front there is message that says determining the coefficient and explain them.
I can't understand what it is that you're seeing. You're not seeing precisely this page that the rest of us can see. Determining stoichiometric coefficients. You're seeing something different. So you're seeing it now. Is it a problem with?
Okay, got it.
Got it? Okay.
Yeah.
All right. Good. Let me move this over here. All right, and annotate. All right, so here's my page. Oops, mouse. So here's the page we would look at. This is basically, if you remember the last experiment we did with this, we had this sort of virtual workbench that we worked on. We would just, click on and drag things over. So we have solutions. And if we scroll down, we look at the different solutions we have. We have water. We have A, 1 molar B, 1 molar C, and 1 molar D. And we have 0.1 liters or 100 milliliters of each one. So why don't we just start with that? Why don't we just put A on each one? Now, one of the things you're going to see is, so this is, you see solution A, and it's got tells you a couple different things. So it gives you the concentration of A and molarity as 1.00000. So you get it's really precise. Molar. What's this? What does that mean? What's this H plus and OH minus? What's that?
Ionize?
Something's ionized. What's been ionized?
Hydrogen and then oxygen and hydrogen.
Well, something's been ionized, and these are the products of it. But where'd they come from? So solution A is in what? Because we don't actually know what it's in, right? It didn't tell us. It's a solution. So a solution means it's dissolved in something.
But I know if it's H positive, that's mean is base, and if OH negative, it's mean if acid.
It's the other way around. Yeah, H plus means acidity. Acidity. And OH minus means basicity. H plus is an acid, OH minus is a base. Where do they come from? So basically, what is A dissolved in? What is the solvent? Because it doesn't say. It just says it's a solution. It could be dissolved in anything. It could be dissolved in hydrochloric acid. It could be dissolved in isopropyl alcohol. It could be dissolved in benzene. I mean, it's just a solution. We don't know what it is. But this actually tells us what it's dissolved in. Where do those come from?
Is it water?
It's water, exactly. And so water, neutral water, what's the pH of neutral water? pH of water that's not acidic and it's not basic.
7.
7, right. So pH 7 means it's a neutral solution. It means it's neither acidic nor basic. So, but where does that come from? What's pH equals 7? What does that actually mean? We sort of talked about it a little bit in class the other day. See if anyone can remember. What does that mean? The pH equals 7 means something. What does it mean?
Positive hydrogens there are.
Right,
Hydrogens?
right. It's the concentration of H plus. That's what pH actually means. The H in pH is this, H plus. And so what it's telling you is that pH 7 means that the concentration of H plus is 1 times 10 to the minus 7 molar. That's what that means. That's where the pH comes from. It means it's 1.10 to the minus 7. If it was pH 6, the concentration would be 1 times 10 to the minus 6. And what we'll learn later, if we actually get to acids and bases, is that the concentration of H plus in pure water, so remember, that means neutral. It means it's not acid and it's not base. So when it's not acid and it's not base, that means that those two concentrations have to be exactly the same. And at pH 7, they're exactly the same. So that means the concentration of OH minus, or hydroxide ion, is also equal to 10 to the minus 1 times 10 to the minus 7. It's exactly the same. So this concentration and this concentration are exactly the same when it's neutral. Neutral means there's no more acid and there's no more base. When the pH drops below 7, that means my concentration of acid goes up and the concentration of base goes down. And we'll learn this later, but the concentrations of acid and base always equal the same thing. They always equal 1 times 10 to the minus 14 whenever you multiply them together. So if at pH 6, if the concentration of acid is 10 to the minus 6, that means my base has gone down to 10 to the minus 8. And when I multiply them together, I get 10 to the minus 14. So what this will show you is that A must be in a neutral solution of water, or my concentration of H plus and OH minus are identical. So that means it's water, and it means it's neutral. So that basically tells you that A is not an acid or a base. So you don't have to worry about that right now, but just don't be thrown by the fact that when you are doing your reactions, you're going to get these things as well. So you're going to get the concentration of A, B, C, D, and H plus and OH minus, which will basically tell you if you're forming an acid or a base. But I'm not worried about that right now. I just want you to worry about what's the product, what are the ratios of reactant that make it, and don't worry about whether it's an acid or a base. We'll get to that later, okay? So that's just what H plus and OH minus mean, acids and bases, yeah. Okay, so here's our solution A. So we go back to the stockroom, and we'll put on some B. Here's the same thing. You can set, so our solution, our concentration of H plus and OH minus are again 1 times 10 to the minus 7, and they're the same, so it's neutral. So B is also a neutral molecule. C, same thing, 1 molar C, neutral solution. Let me go back to D, and it's also neutral molecule. So none of A to D are either acids or bases right now. So go back to the stockroom, and now we need something to pour them into, right? We just can't have them pour them on the floor. So go to glassware, and beakers are fine. And you can select any size you want, doesn't really matter. If you want to add all of them at once, just make sure you pick something that's big enough. I'm just going to put them in a 250 ml beaker. So this will be the first reaction I do. I'm going to look and see what we get out of it, and then basically I'm going to leave you guys to then figure it out. And you can, I'll obviously give you some time to ask some questions. But what I'm going to do is just add equal amounts of A, B, C, and D and see what we get. Because basically the reaction's got to be somewhere in there, right? If we add all of them together, something's got to happen. And then we just have to figure out by, taking one away, taking two away, seeing which is the reactants and which is the products. But right now we should be able to tell which is the reactants and which are the products. Maybe not the ratio so much. So A, I'm going to put in, see, so how much A should we add? Any suggestions?
10 millimeters?
How many?
10.
10? 10 milliliters, right? 10. So I just put in 10 and hit pour. So that gives me exactly 10. If I put in realistic and click on pour, I basically just keep adding A until I stop. Right now, I want to know what my volumes are. So I'm going to be precise. So 10. And then to let me know that I've added A, I'm going to move A down at the bottom. So that lets me know I've added A already. So then B, I'm going to put same amount, put 10 mils of B in. And hit pour. And then put my B down at the bottom. Let's put this right in the middle. And then C, I'm going to add my 10 mils of C. And pour. And then move my C down to the bottom. And I'm going to put 10 mils of D in there. Pour. 10 mils of D. And then move my D out of there. All right, now let's see what's actually left in there now. So it would appear that so what are my expected concentrations of A, B, C, and D in this situation?
0.25 molar.
Right, exactly. So what I should see, if nothing happened at all, is I should see 0.25 molar A, B, C, and D. It should be the same, 0.52 molar for all of them, right? But that's not what I see. Oh, and have a look at H plus and OH minus. They're still equal, right? So basically that means I have not created an acid and I have not created a base. Because if I created an acid or a base, those concentrations would change, but they haven't. So you don't even have to worry about that. But what's happened to the concentration of A and B?
It didn't change.
Well, what did I expect? Remember, I expected this. Is that what I'm seeing for A and B?
No, it increased.
They increased? Take a look. What is E to the minus 9? What does that mean when you see that? What does E to the minus 9 mean? Maybe you haven't seen that before. If you see that in your calculator, what does it mean?
Is it a -9?
Yeah, this is -9, but what is E to the -9? What does that actually equal to? That's equal to a number.
9 times 10 to the -9.
That
The
means
dimension, the
1 times 10 to the minus 9. That's what that means.
Mhm.
E to the minus 9 means 1 times 10 to the minus 9. So we look at A and B. We look at A and B, and I was expecting 0.25 molar A and B. What I'm actually seeing is 7.75 times 10 to the minus 9 molar. So has it gone down or gone up?
Yeah.
It's gone way down because this actually equals, what does that equal in scientific notation? 0.25. You were to write that, this is good practice for your test next week.
2.
Times 10 to the what?
Hold on. -1.
Right, -1. So my I expected to see 10 to the minus 1 molar. I actually got 10 to the minus 9 molar. So that means much, much less. mean, basically, it basically means I've used all of it. I mean, it means there's a vanishingly small concentration. Because basically it means my concentration has gone down by a factor of 1, 2, 3, 4, 5, 6, 7, 8. It's gone down by a factor of 100 million. So it's 100 million times less concentrated than we expect. That's basically gone, right? I mean, that's basically zero. If it's gone down by a factor of 100 million, it means it's barely detectable. And so for all basic purposes, we can say that A and B are both gone and that they've been completely consumed. What else can we say from these concentrations? So if we could say that after this reaction, A, oh, well, man, I can't really see that at all. Let's do this one. So A is basically gone. B is basically gone. What's happened to C and D?
They've increased.
They've increased in concentration, right? Remember, this molarity is molar. So this is 0.75 molar, and C is 0.5 molar. And what was the concentration we were expecting? What should the concentration of C and D have been if nothing happened? So no reaction.
Should have been 0.25.
Right. With no reaction, our concentration should be 0.25. What's our concentration of C?
0.75.
No, that's D. D is 0.75. Concentration of C is what?
0.50.
Right. So C is now 0.50 molar, and D is 0.75 molar. So basically, how much, so if C, so we created some C and we created some D, right? How much, now the question is, you need to figure out how much C was created. What's the concentration? Basically, let's look at, so we have C original versus C created, or C new. Let's look at C new. So our original concentration of C is this, 0.25 molar. What's the concentration of C that was created?
0.25 plus 0.25.
Exactly. No, wait. What's the concentration of C new?
0.
Concentration of C that you made.
0.25.
Right. So this is the concentration that you added, and this is the concentration that you made. And when you add them together, you get the final concentration. So let's look at D. You expected 0.25 molar, and yet you got a concentration that's now 3 times as much. How much D was present that you put in, and what was the concentration of D that was created? What's the concentration of D that was created, the D new, or D that was formed? 0.5 molar, right. So basically use those concentrations, concentration of D created, because that's your product, right? This is the concentration of C that was created. Use that. That tells you that with this amount of A and this amount, basically it means 1A. So your simplest solution from here would be 1A plus 1B gives you how many C and how many D? That's basically what we're looking for, okay? So then go back, figure out that's the simplest. Try some other combinations and see if If you add more A, what happens? If you add more B, what happens? Do you get more product or do you get less? Or do you get the same? So basically this will sort of let you be able to figure out what the stoichiometric relationship, what are the coefficients between products and reactants. So what your table should look like, let me go back to the,
That's a quick question.
oh,
before-
yeah.
So,
Oops.
you were saying 1A plus 1B equals would be
Yes.
25C plus 50D?
No, because we're looking at molar ratios, not concentration, right? So basically I'm saying I added 1 mole of A and 1 mole of B. How many moles of C and how many moles of D would that give me? Okay.
Would you do the percentage of it to get it?
No, you'd actually look at the number of moles. So you have to calculate the number of moles. So our final volume here, so we've added, our final volume is in the beaker. So it basically tells you what your final volume is. It's 40 mils. So figure out how many moles of A you added, how many moles of B you added, and then how many moles of C were created and how many moles of D were created. And that will give you your ratio, and that'll give you your coefficients. Okay, do you see what I mean?
So you have to find the mole of A, B, C, and D.
Right,
And then once you find it, then you could find your coefficients.
exactly. Because the ratio of those moles will be the coefficients you need. So work it out for this, and then start doing different experiments to add more A, add more B. Do you need, just don't add C or D at all. And basically what your last reaction should be is the precise amount of A and the precise amount of B, where they're both consumed entirely and you get nothing but C and D left over, okay?
Nothing but C and D left over, right?
Well, it looks like those are your products, so you don't need to add them. So you can basically, or maybe you do, maybe you need the presence of, you might find out that the presence of C is necessary to make D. So figure that out too. You might need C to make D. So if you leave C out, does it still get created? Does it still make D? Maybe the presence of one is necessary to make the other one. Don't know until you actually do the experiment.
Okay.
So take things out, change the ratios, and then see what's the smallest amount of each one you can add, so that all your reactants are gone. There's basically nothing that you added at the beginning is left at the end, and then what's left, and then what do you get at the end?
So another question is it, so each person will have a different end result, right?
I don't know. I wondered about that. What I'm going to do afterwards is I'm going to do this again and see, because I did this like a week or so ago. I want to check and make sure I got the same answer. What I'm kind of hoping is that everyone gets a different one, or else this is going to be way too easy, you know. So I'm hoping that everyone gets a different one. I don't know whether or not everyone will get the same one or not.
Because when I followed along with you, I'm getting a different.
Oh, good. So I think everyone's will be different. That's what I want. I want everyone's to be different, because if they're all the same, then yeah, you can just like say, you know, call up each other. What did you get? I get. But now you have to figure it out for yourself.
I have another question. How can we tell which one will end up being the product?
Oh, well, in this instance, let me just clear. Where's my clear? In this instance, we can see when we added, this is the first experiment I would do. Add all 4 of them, right? Just see what's up. So in this instance, I've added all 4 of them together. And my concentration of A and B went down. So my concentration of A went down. My concentration of B went down. My concentration of C went up. And my concentration of D went up. This already tells me that A and B are reactants because they're consumed. There's less of them at the end than there were at the beginning. Therefore, they're reactants. These two tells me that since they went up, C and D must be products because the concentration of them both went up. What I don't know is what's the actual ratio of A and B I need precisely, and do I need the presence of C and D there for the reaction to proceed? It could be that if they make C and then actually C is a catalyst for the production of D, or I might need it there at the beginning. I don't know. So what I'll do is I'll change things around. I'll add, just A and B by themselves. Do I still get C and D in the same amounts? Then, I'm pretty much done at that point. But if let's say I make C, but I don't make any D, that probably means, well, then I need a little bit of C there at the beginning. Maybe I don't know. But what I can say definitely is that A and B are definitely reactants. There's no doubt about that.
If I created the products and then in the end result A and B equals 0 molarity, that basically means.
Yeah, and this is basically 0. I mean, it's gone down by a factor of 100 million. So I mean, that's basically 0.
We just have to figure out the exact 0. Is that what you're saying?
No. I'm saying that this is basically, that's 0, basically.
Mm-hmm.
It just means there's just a vanishingly small amount. Basically, it's 0. 10 to the minus 9 is basically there's just nothing. I mean, if you're like we showed before, if you're expecting 2.5 times 10 to the minus 1 molar, and instead you get 10 to the minus 9 molar, that's basically 0. It's basically nothing. It means that you've used 99.99999% of the total. And I'd say that's pretty close to 100.
Professor,
Yeah.
how to change A and B and C and D? I saw in your screen still it has the same volume. Then how you?
Sorry, what was the question?
I said I have the same volume in my beaker, the same like.
Yeah, 40 mils, right?
Yeah, but my answer in the table for A, B, C are different.
Yeah, because your reaction's different than mine.
Oh, then
Everyone's reaction's different. So look and see if the concentration goes up, the products. If the concentration goes down, the reactants. And then figure out what's the ratio of your two reactants. What do they need to be? Because here, basically, A and B were both consumed completely. So that tells me they probably need to be there in the same ratio. Either it's 1-to-1 or it's 3-to-3 or it's something. It's the same ratio. I need to actually figure out the number of moles of C and D that are created to figure out what this ratio is. But it's going to be the same. It looks like A and B need to be there in the same ratio. I just don't know what the ratio is. 1-to-1 or 3-to-3 or 4-to-4. I don't know.
Okay, Professor, in my reaction, I saw B and A is same, equal, D is 0, and C, it's not negative, it's 0.125. I mean,
yeah, so that means your D has been consumed completely, and that C has been consumed somewhat.
0.125, but it's not negative, like still.
No, it means it's 1/2 of what it was, meaning you've consumed half of your C and all of your D. So basically, what you need to do is, if your expected concentration is 0.25 molar, go from there. If you created product, it's going to be higher than that. If you've removed reactant, it's going to be less than that. And that'll tell you what your reactants and your products are. We can talk more about it at office hours tomorrow. Anybody else have any questions? So, let me go into what I'm looking for here. Let's clear everything. So basically, what I'd like to see is yeah, what's the smallest combination of chemicals required, and some sort of table as to what you're. There should be some kind of table, even though I didn't like spell it out. I always want a table because you're collecting data, right? Anytime you're collecting data, you should automatically assume a table's required. So it should have a table, something like amount of A, B, C, D, how much you added, what the volumes were, and then what the concentrations were after. And so your last one should be, you know, I added 20 mils of A to 30 mils of C, and at the end, my concentrate, I only got, you know, a certain concentration of D. So that will say that, like, you know, all my A was gone, all my C was gone, and it all went into the production of D. So that's what your table should just have, you know, volumes, A, B, C, and D, and then concentrations.
I have a question.
A, B, C, and D. And then
And
trial 1, 2, 3, 4, however many it takes. Yeah.
And do I need to include H and OH in the table?
No.
Okay.
No.
I have a question. What does it mean if my A and B are like 0?
That means they've all been, so you added all A, B, C, and D.
Yeah, and then my A and B are just 0.
So what do you think happened?
It stayed the same.
No, if they stayed the same, what would the concentration be? If nothing happened to A and B, what would the concentration of A and B?
Would it be 0.25 molar?
Right, it'd be 0.25 molar. If you added the same concentration, the same volume, I mean, of all 4 reactants, your baseline concentration should be 0.25. In other words, 0.25 molar. If nothing happened to that particular chemical, that's the concentration you should have. So if you got a concentration of 0, then what happened to that chemical?
It's a reactant.
It was consumed. It was turned into something else. And so it's by definition a reactant. Right?
Yep.
So that would be like, you know, so that would be trial. So in my table, I would have trial number 1 and volume. So I would say 10, 10, 10, 10. And then of course, remember mils, because it's got to have, and then this would be molarity. So then for my A and B, I just have 0 and 0, and then give whatever C and D is. So then my next trial would be, I'm changing something to see, you know, to see exactly what I need to add so that there's nothing, no reactants are left over, and there's nothing but product at the end.
So I have a question. If it's
Mhm.
0 reactant, like the case that he had of A and B,
Mhm.
and I had a product C and D, that means that basically it's set. I just have to find the coefficients.
Yeah, pretty much. Yeah. I mean, if they were both consumed entirely, like the one I had here, mine. I don't know why you got 0 and I got a small number. That's weird.
Yeah, I want to ask you, if I got 0 or if I got small number with minus, that's mean same
That's
meaning?
the same. Yeah. I'd say
Okay.
it's the same thing.
What's the meaning?
Yeah. The why I'm getting a small number and you guys aren't. I don't know. Why? Uh-oh.
So your A and B would be basically the reactant.
Yes. Yes. Wow. I'm trying to share and it's not sharing.
So would
Wonder
it
if that-
mean you just have to find the coefficients and you're done for you? Or are you trying to
Pretty
figure
much, yeah. So then I just need to figure out what the ratios are, because all that tells me is that the ratio of A and B are the same. So however much A, that's how much B. But I don't know if it's 1 to 1, or if it's 2 to 2, or if it's 3 to 3, or 4 to 4. I don't know what that is. I just know that they're the same. I need to figure out how much product I made in order to determine that.
Can we do the coefficient and the ratio for your experiment so we got idea to practice? Like how you figure out the coefficient and the ratio in your data? So we will...
No, I'm going to let you do that. That's the point. That's the point of the experiment. That's the point of the experiment.
Okay.
Is to, find this out for yourself.
Okay, another question. For I have to choose 3 times, to repeat my experiment 3 times, correct?
Oh, as many times as it takes.
No, I mean to write in the report.
No, you should. I mean, it's virtual. You should get the same. I mean, you can repeat it again, and if you get exactly the same result, then I wouldn't bother reporting it. I mean, you should get the same every single time.
So I have a question, Professor.
Yeah.
My C, I had 0.125.
Mm-hmm.
Not exactly 0.
Mm-hmm.
So, and it's not exactly a negative number. So would I continue?
Well, it's not going to be negative. Just remember, when we say negative, negative just refers to the coefficient, to the power of 10.
Yeah.
So
cases like
so
that,
your original concentration was like, 10 to the minus 1. And then if it goes down, it'll be 10 to the minus a bigger number. It's not negative. Concentration can never be negative. It just means less.
okay.
Yeah.
So in cases like that, if I have 0.125,
Mm-hmm.
Would I just play with the C until C becomes either 0 or a lesser coefficient?
Yes. Yes. Yeah. Tweak the coefficients until your last reaction, like I said, should be, I added, so under volumes and concentrations, so I've got my A, my B, my C, my D, and then under concentrations, I got my A, my B, my C, my D. Let's say that in your particular instance, so C looks like it's a reactant, right? And something else probably, I don't know, whatever it is. Let's say A is a reactant. So you need to figure out, so I'm not adding any B. So you need to figure out, so let's say the ratio is 2A plus 3C gives 1D or something. Of course, you wouldn't add the 1, right? So so your final experiment should be 20 mils or whatever. 20 mils of A plus 30 mils of C, and then the concentrations at the end would be none of A, none of B, none of C, and then whatever the concentration of D would be. Okay, so this basically tells me that all the A was consumed, all the C was consumed, and the only thing I got left the only thing that should be left in the beaker or the flask, whatever you used, should be D and nothing else. So this could be 40 mils and 60, whatever just as long as the ratio is the same.
How do we check our work to make sure, like, once we get that result?
Well, that's what you should see. Your final experiment should have nothing left but product. There's nothing else there. So if your product is both C and D, don't have any C and D added at the beginning, and just have C and D at the end. So basically what I'm looking for is that your concentration of product at the beginning should be 0. The concentration of reactant at the end should be 0. So that tells me that you added the precise amount, the precise ratio of reactants to get the maximum amount of products. That's what you will see. When you have the ratios just right, there'll be no products at the beginning, and there'll be no reactants at the end.
And I can change this concentration by changing the volume or what?
Yeah, you can't change the concentration. They're all 1 molar, right? All of your chemicals are precisely 1 molar concentration.
Yeah,
So all you can do is change the volumes. You can't change the concentration.
Yeah, I mean, like, you want me to change the concentration, the volume either for A or B or C. It depends my.
Right. If you're so in this instance, in her instance, A and C were her reactants. So basically, what you would do in that instance is change the ratio of A and C. Change 10A to 30B or C, 10A to 30C, 10A to 40C. What ratio of those two leave you with no A and no C at the end? So there's neither one of them is left over. So if they're both completely consumed, that means that you've got the ratio exactly right. Because if there's either one of them's left over, that means one is in excess and the other one's limiting. And the one that's in excess, you'll have left over at the end. So you don't want any left over at the end. You want your volumes to perfectly match the ratios.
So I have a question. Do you want it exactly 0 or
whatever, or 10 to the minus 9 or whatever it is, because that's basically 0.
Okay.
I don't know why I'm getting like this tiny amount left over, but that's basically 0.
Okay, what I understood from you, that in the final, the column of molarity, that one has these numbers, I have to make it to equal 0, correct? Like
Your reactants.
I mean, I will
Your reactants should be 0 or very, very close, like minus 9 or whatever, and should only have concentration of products.
Yeah, how can I know it is 0 now?
Well, it's either, when you add them together, it's either you're going to get 0 or you're going to get a very, very small number.
For this molarity, for this table?
Yes.
So it's gonna be all the value of A and B and C and D. I should have all are 0.
No, because you're going to have, one of them's going to be a product. So that's going to have a positive, that's going to have a concentration. You can't add all of them together. You can't add A and B and then like nothing happens. I mean, they make something. If you figure out that so in this instance, A and C are reactants, they got to make something. They either make B or D or both of them.
So
I do not understand how I can make the reaction is 0. From where?
No, the reactants. You want the reactants,
Okay.
the concentration of the reactants to be 0 at the end.
Yeah, but how can I decide which one is the reactant?
At the beginning of when you add all 4 of them at the beginning, the very first experiment you do, add all 4 at the same volume. If the concentration at the end goes up, they're products because you've made more. And if the concentration goes down, it means you've consumed them. So they're reactants.
That means from the beginning, I have to know which one is the reactant, which is the product.
You should be able to figure that out from the very first experiment.
Then base it on.
And then work on the ratios.
Professor, I have another question.
Mm-hmm.
Then should we make, so like, let's say if we added too much of B, should we make a duplicate to restart it, or of the beaker? Because we can't really.
Just empty it, or you could either empty it or remove it, and then replace it with a new one. Each reaction, obviously, you want a new beaker. Yeah. You don't want to have that other stuff in there.
Using with the same beaker, right?
Yeah, you can just right click and just say remove and then add another one. Or I think you can right click and just say empty.
Oh, okay.
Either one.
Okay.
Yeah, I'm desperately trying to get back to sharing that, but it will not let me. Oh, here we go. Yeah, I can't. What screen are you guys seeing? Are you still seeing the instructions, or are you seeing the web page?
The virtual lab.
You're seeing the virtual lab?
Yeah, you just erased it.
Yeah. Oh, no. Is it the instructions or the lab itself?
Workbench of the lab.
You are, yeah, because I'm not weird, because I'm not seeing it. That's interesting. Okay.
So we basically have to do it one sitting because we can't come back to it because it'll be a different.
Right, because you might get a different one. Yes, you got to do it all at once. So yeah, so when I right click, I can remove the liquid, and then yeah. So that way you don't have to
It's better
like get
to
rid of it and replace it. Yeah, just right click and say remove liquid, and then you can see there's nothing in there. And then I can add my A, my B, my C, and my D again.
okay. So it makes sense to do your table along with it, so you can keep
Yeah,
track, right?
yeah. Excuse me. So yeah, it's just going to be fun. You get to play around, and I'm glad to see everyone's getting a different one. That's good. I was worried because I think this one looks an awful lot like the one I did before. So I was a little worried that there was going to be the same one, but it isn't. So good.
Yeah, like every time you refresh the page, you'll get a different answer.
It looks that way. Yeah. So don't refresh the page.
I have a question for post lab.
Uh-huh.
For number 3, when for a catalyst, what does it mean when it says like it gave the definition of a catalyst, but
Mhm.
what does it mean when it says like remains unchanged?
Oh, it means the concentration's the same.
Oh, okay,
Here,
okay.
let me give a whiteboard here. Let me clear that. So if you had a catalyst, basically, let's say C was a catalyst. Okay, so that would mean that I would add A plus B, and nothing would happen. So I just get nothing. So, but then let's say, so my concentrations of A and B would both be the same. Well, they would be like 0.5, right? If they were 1 molar at the beginning, then I add them both together and they're both 0.5. So nothing happened. But let's say at this time I added A plus B plus C, and I looked at the concentrations. So now my concentration of A is 0. My concentration of B is 0. My concentration of C is 0.33 molar, and my concentration of D is 0.33 molar. So what can I say happened? Basically, it means that all of the A was consumed, all of the B was consumed, nothing happened to C, and then they made D. So what I would say is that A and B are reactants, and that C is a catalyst, because C was there at the beginning. It's sort of like a spectator ion. C was there at the beginning, and C was there at the end, and the amount of it did not change. But its presence is absolutely essential for the production of D. And so the way I would write that is 1A plus 1B gives me 1D, and you put the C here. Basically, the C just there is telling you that C is essential for that reaction to take place. And that there may have been, like the reactions in your body, the catalyst undergoes, most of the time, the catalyst undergoes a chemical reaction, but it reacts forming something else. Let's say the reaction is A plus B gives you a CD, that's the product, and then this bond between C and D breaks. And at the end, so then you get C plus D at the end. So basically what I'm saying is that your reaction would be A plus B plus C gives you C plus D. And so since C went into the reaction and C came out of the reaction, we say it's not really a part of the reaction because you didn't create nor destroy it. So that would be a catalyst. Even if it gets chemically changed during the reaction, as long as it changes back at the end, it's a catalyst.
So catalyst, it means if it is in as the reactant, it will be also as the product. I will see this. I will see C in the reactant and in the product.
In the same concentration.
Yeah. Okay.
And it's essential for it to be there. Just because I add A plus B plus C and get C plus D at the end doesn't mean C is a catalyst. That does not mean that. It only means that if I add A plus B, and I get nothing. If nothing happens in the absence of C, that tells me that C must be present in order for the reaction to take place. So catalyst means two things. It must be present for the reaction to take place, or really what it does is a catalyst just speeds up a reaction. The reaction will still take place, but it may take billions of years to happen. And in the presence of a catalyst, now it takes seconds. So it doesn't actually, make the reaction happen where it wouldn't have. It just speeds it up tremendously. So this tells me that A, oops, let me go back to the whiteboard. Oh, sorry about that. This tells me that A and B will not react without the presence of C. So that means that C is a catalyst. If the concentration of C is the same at the beginning and the same at the end, that means it's a catalyst. Because if the concentration of C changes, that means it's a reactant too.
Yeah.
So would that mean it's an excess of C? Or no?
Well, yeah, you would say that. It probably means you could add a lot less C. That's true. You could probably add, because generally a catalyst means you only need it in a vanishingly small amount. So you could add 1 molar A, 50 mils, and 50 mils of 1 molar B, and maybe you only need like a mil of C. Maybe you only need a half a mil of C, or some really small amount. I mean, that's something to see, that if it appears that you need C for this reaction of A and B to go forward, it actually would be interesting to see, well, how much do I need then? If it's a true catalyst, you would need barely any. You'd need a really small amount.
So in that case, would we have to find C being the lowest coefficient?
No, I would just say no, because it wouldn't be a coefficient, because if its concentration doesn't change, it's not a reactant. And we only include coefficients for reactants and products. Catalysts we don't, because they're not actually part of the reaction. We put them up here, right? We put them on the arrow. We do not include them as a reactant, and we don't include them as a product if it's a catalyst.
So this is only if the concentration doesn't change.
Right. So remember, two things. It needs to satisfy two criteria. Concentration doesn't change, but it's also essential for the reaction. If you don't need it for the reaction, it's not a catalyst. And generally 3, it's not always the case, but like 99 times out of 100, it's the case that you need it in really small concentrations. That's not always true, but it's generally true. You don't need a lot of a catalyst to make it work, to make the reaction go. All right, any other questions?
For lab report, do still
Yeah.
I have to do the same way, like a purpose, then?
Always the same. Yeah, those never change.
Okay, for conclusion.
That's a general. Well, your conclusion would be, this is the. I determined that the formula for the reaction is 3A plus 2B equals D, and I proved this by doing the experiment, changing the ratios. That would be your conclusion.
Okay, how about the discussion?
Well, discussion and conclusion, yeah, I mean, you can basically put them, those two can go together.
Okay.
Yeah, it basically means the same thing. All right, I will have office hours at 10:30, and we'll have a recitation, the fun recitation, the one we were going to do last week, about electron configuration. We're actually going to do this week. And then lecture, I'll see you guys at 4:15.
Yeah.
All right, have fun with this one. Let me know if you send me a note if you have any questions about it, okay?
But just a last thing I want to ask you, could you please post that video for this lab and like in this couple of like now, or I mean before the lab exam, so we will review the
Oh, sure. Yeah. That's a good idea. Yeah.
Thank you.
Yeah. Yeah, so the exam will just be on the first 4 labs. We're gonna do another one on Wednesday, but it won't be on that one. Okay?
Thank you so much.
All right. We will see you in a little while. All right, bye-bye.